Chapter 24, OpenStax Physics, College Physics. These are the presentation slides that go along with the chapter. I made a chapter summary, but I wanted to just show you some of the pictures. I'm going to go through this very quickly, and then I'm going to show you how we make visible light, and because I think that's fun. And then I'm going to show you some infrared images, and they're partially overlapping, and that's not what I wanted to do. I want to do that right there. Okay, so let's just skip through that. This is a radio. It's not really a radio telescope, but the point is, in this image, they want to talk about electromagnetic radiation, and just because something has a longer wavelength doesn't mean that it still acts like light, because it is light. And we'll see this when we look at concave mirrors, that this is a mirror, okay, in the radio spectrum. Maxwell Clerk, that's him. This is the setup that they use to detect electromagnetic radiation. You get an oscillating circuit here that produces a oscillating potential difference between these 2 points that makes a spark. That spark produces an electromagnetic wave. You can detect that with this other thing. So it was kind of a big deal to detect that. It shows that changing electric and magnetic fields produce changing electromagnetic fields that you can then detect. And so that was your first radio wave. Now, the key thing here is that the calculated speed of these based on Maxwell's equations is the same as the speed of light. And that's how they knew, hey, maybe this electromagnetic wave stuff is the same as visible light. Now, there is a good PhET simulation. I'm not going to pull it up, but it shows these. How do you produce electromagnetic waves? You always produce electromagnetic waves with accelerated charges. So here's a radio antenna. If I accelerate those charges up and down, they'll produce changing electric fields that make changing magnetic fields, and boom, that's an electromagnetic wave. So you could also, this just shows how you explain those changing electric and magnetic fields to produce the magnetic fields too. But this is a good picture right here. So this shows the direction of oscillation of electric fields, the direction of oscillation of the magnetic fields, and the direction the wave travels. So in general, if you take your right hand and let your fingers cross through the electric field and then the magnetic field, your thumb points in the direction that it travels. This is the electromagnetic spectrum. I'll get to this later because I have a better picture, and we'll talk about it. I have no idea what they're talking about there. This is just how to detect longer wavelengths with a longer antenna. This is for how do you communicate to things that are underwater. This is kind of cool, not super important, but it's kind of important. So how do you transmit sound data, audio data over an electromagnetic wave? And that's what we do with the radio waves. So AM radio, the frequency of the electromagnetic wave is way too high for humans to hear. Okay, so what we do instead is we have a carrier wave, and then we adjust the amplitude of that carrier wave so that it matches the frequency of the sound. Now, the one trick you have to do here is that if you didn't do something, you would get as much up and as much down, and you can't hear that because it's still a high frequency thing. So to cut off this bottom part, you have to use a diode. A diode only lets electric current go one way and not the other. And this is, if you think about a crystal radio, that's what the crystal does. It only allows the current to go one way, so you cut off the bottom of that wave. This is an FM wave. AM stands for amplitude modulation. FM stands for frequency modulation. So you take a carrier wave of a particular frequency. This is the frequency of the radio station. Then you adjust the frequency a little bit based on the amplitude, based on the frequency of the sound, the audio signal that you want to change. So it's a non-constant frequency, but it's based around this carrier wave frequency. And then you can set up a circuit that takes this and produces the audio back. So it's a higher frequency starting with. FM radio waves are much higher frequency in the megahertz, 100 megahertz, and which you can't hear, but that allows you to send more audio signal through it. Those are radio towers. Yay. That's a radar image. Don't really visible. This is the visible spectrum. We'll talk about that. Ultraviolet image. Ultraviolet image. How do you make X-rays? Remember, you have to accelerate charges. And so to make an X-ray, if I accelerate a charge in an atom, then I can, if the acceleration is the right frequency, then I can get an X-ray. But I don't really want to talk about that too much. Here's another way to make X-rays, is to make charges slow down. So a classic X-ray machine takes electrons and bombards them into something like tungsten, and when they slow down and stop, they produce X-rays. X-ray. I'm going to actually talk about X-rays. That's not important. Not important. Electromagnetic waves are still waves, so they can constructively and destructively interfere. We'll talk about that more when we talk about diffraction. That's just an antenna. That's fine. Okay, that's it. Okay, I don't want to do that anymore. I want to talk about, let's go over how do we make light. Not that one. Open recent. I just had it open. How lights. And then I'm going to show you this infrared stuff. Okay, so this is the electromagnetic spectrum. I kind of like it better. We have over here very, very, very long wavelength electromagnetic waves, very short, so it goes radio, infrared. There's microwave in there too. Visible light's the super, super, super tiny part that we can see with our eyes. Ultraviolet, X-rays, gamma rays. Now, one of the things that you'll see on here, it says energy. Okay, and it says, oh, well, shorter wavelengths like gamma rays are higher energy. That's not exactly true. They interact with matter on a higher energy level, but you don't have to have high energy gamma rays. You can have super, super high energy radio waves, high intensity radio waves. A radio station has a very, very high output, power output, okay? But they're very long wavelengths. It's just they interact with matter at a lower energy, okay? How do we make light? At the atomic level, we have to accelerate charges. And one way to do that is to take an atom, and if you accelerate charges by having it change energy levels, and atoms have quantized energy levels. There's only certain energy levels. And that's kind of a big deal, but it means that this particular element, when I excite it, produces a change in energy that's proportional to the change in energy levels, and that gives you a particular frequency. So different elements produce different frequencies of light, and they only produce those frequencies. Now, there are other ways. If you smash atoms together in a solid, then there's a bunch of different variations of these energy levels due to interactions, and you can produce all the different wavelengths. But an isolated gas will just produce certain frequencies. Here's a picture of that just so you can see. Here's one particular element, I have just these 3, 4 energy levels, and these are all the different energy transitions I can make. Here's a different element with different energy levels, and you'll notice that they have different energy transitions. So these two would produce different frequencies of light. Now let's talk about some of the ways that humans make light, and here's the first one that we didn't make, the sun. So the sun produces, and I took that picture. The sun produces light, and I have this little thing over here. I don't want to do that. Let's see. Let's just make this. Oh, it's not, because it's not playing. Okay, how's that? Now it's too big. I'm not a very prepared person, am I? Okay, there's the sun. The sun produces light because the surface is hot. That's it. Hot things, when you get things hot enough, they produce light in the visible spectrum. And the surface of the sun is super, 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 super hot, so you produce light. Why is the sun so hot? Not because it's burning. It's not on fire. It has nuclear fusion in the core that produces lots of energy, and that makes the surface hot. And we could talk about the sun for probably 8 years. There's so much to talk about, but that's just one way that we produce light. The moon, we like to think of the moon as producing light, but it doesn't. It's just light reflected from the sun. I assume you knew that. This is Venus, also light reflected from the sun. So here is fire. I took that picture. Fire is one of the earlier ways to make light. The basic idea is to take something with carbon in it, to have a chemical reaction with oxygen to produce carbon dioxide and other stuff. And that produces energy, and that energy can make things so hot that they glow. In the case of a candle, the flame is unburnt carbon particles that get really, really hot, so hot that they glow, just like the surface of the sun. This is an incandescent light bulb. The idea is to have a wire. There, you can see the wire right there. And as I run electric current through there, the wire gets hot. It gets so hot that it glows. So in this case, that's just an electric wire, a wire with current going through it that gets hot. That's it. It's the simplest way to make light, and it's just so cool. or hot. Now, why I took that picture? Why is it surrounded by glass? That's to keep the air out. If you get oxygen in there, the filament will burn and melt, and then it'll break, and you won't have light anymore. This is a neon light. So a neon light, I took that picture. And I took all my own pictures, right? So I don't have to worry about stealing other people's pictures. A neon light has a neon gas in there, and that gas, that element of gas, when you collide electrons through air by applying a voltage, the electrons accelerate, they collide with the neon gas gets excited itself, and when the electrons come back down to the ground state, they produce a particular frequency of light, neon colored light. So if you see other colors of neon lights, it's not neon. We still call them neon lights, but that's a neon light. Now there's another way we can use lights, because a neon light is a lot like a fluorescent lamp. In a fluorescent lamp, we don't put neon in there, we put some gases in there, including mercury vapor. Now when you excite an electron and you collide into the mercury vapor, it gets excited, it produces ultraviolet light. That ultraviolet light then hits an outer coating on the outside of the tube, and then that has another interaction that produces light. I'll show you how that works. But here's a compact fluorescent. You'll notice it's got a tube a lot like a neon tube, and it doesn't have neon gas in there. It has mercury vapor, and you're creating that mercury vapor. If you remove the outer coating of a fluorescent tube, you know what you get? An ultraviolet lamp. A black light is the same thing, right? That's where you can get those tubes that fit your fluorescent lights, and you have ultraviolet lights. It's the same thing. It just doesn't have the fluorescence on the outside. Here's how fluorescence works. If I have a system like this, I can excite an electron from the ground state up to way up here. And what happens is that it's not able to make the transition back down. If it did, I would produce this jump, which is from ultraviolet light, and I'd get back ultraviolet light. Instead, it makes multiple jumps down, and most importantly, this jump right here is a lower energy level, so it's a lower frequency, and it happens to be in the visible spectrum. So you use ultraviolet light, you excite to higher energy levels, and then it's forced to make multiple transitions down, and some of those are in the visible spectrum, so you can produce lots of colors of light that way. And that's why it's called a fluorescent bulb. Not because of the electron thing, or it'd be called neon, or mercury vapor bulb. Okay. Here is a light emitting diode. These are blue, and this does the same thing. It has an electron energy transition, but not at the atomic level, instead at the solid state level. I'm not going to go through all the details. This awesome picture by Veritasium, I'll put a link to his video because you should watch this on how the blue LED was created. But imagine we have electrons at a higher energy level that jump down to a lower energy level, and then they produce light. This is an arc lamp. I'm going to show you an actual arc lamp. The idea is to essentially burn carbon with a high current. And here I have two carbon rods, and if you get them just the right position, you can produce very, 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 very bright light. So they're useful for things like they were used for movie theaters, because you need a very bright light to project onto the screen, or search lights. They would use these carbon lights. Okay, let's go to thermal window. Do I have it open? Yeah, right here. Okay. So it's talking about vision and how we see things. There's Superman with X-ray vision, which is kind of weird. There's the Mandalorian with his, quote, infrared vision. It looks like that. And then you can't see him because I blocked you. Legolas, he can see really far. So there's these superhuman vision. I made this for something else. And then there's radio telescopes too. The whole thing is just too big. Let's just make this. That's better. Okay. Oh, and that was a picture too. So here's the electromagnetic spectrum. We have radio waves, microwaves, infrared, the very, very tiny sliver of electromagnetic radiation that we call visible light, ultraviolet, X-rays. So how do we see things? Here's two ways that we see things. Number one, on this side, I took that picture. This is a street light. It produces light. That light enters our eyes. This is a flower. I took that picture. Light reflects off that into our eyes, but it has to have light coming into our eyes in order to see things. So here's a light source. It can either go straight into our eyes or it can reflect off of something, and both those are the two ways that we see things. And where I've already talked about this, I actually already used that picture, which I took, fluorescent lamps. Here is the cool part. The element in an oven, when you turn it on, it starts getting hot, but you can't see it. Eventually, it gets so hot that it glows. It moves into the spectrum where you produce electromagnetic waves that you can detect with your eyes. But at the lower temperatures, you can still detect those waves, just not with your eyes. You have to use an infrared camera. And so this is what happens. It's called an infrared camera, or infrared, because what Sir William Herschel did was to look at the different temperatures associated with different colors. So if you take light, white light, pass it through a prism, you get the rainbow of colors. And then he put thermometers at the different colors to detect the temperatures and measure them. And what he found was this bulb right here below, which I drew it above, you can flip the whole thing over, below the red still got hot. And so he called that infrared, even though you can't see it. These are two different infrared cameras. These are both me. This is the FLIR 1, maybe the FLIR 1 Pro. It attaches to your phone, and it's not too expensive. I love it. You can take really great pictures. This is one that FLIR sent me to borrow. It is not cheap at all. It's the complete opposite of cheap, but a much higher resolution camera. So I actually took this picture with that camera. Now, one of the things that we have with infrared cameras is this idea of false colors, because it's infrared wavelengths, right? We can't detect with our eyes. So our brain doesn't know what to do. So instead, the computer chooses to make a relationship between color, false color, and wavelength. And it doesn't have to be the temperature, but that's how it looks. So in this case, this scale right here, it says this temperature up here is 89.7, I'm in Fahrenheit, down to the coldest temperature of 70. So that's 70 and that's 89 point whatever, and if it gets too hot, it's just white. And you can adjust this scale that you put that false color on, right? But you can see the hotter things get brighter and yellower. You can change the color palette too. But this is a computer plug, and you can see they do get hot. All the wires get hot. So that's kind of cool. Here is a dog. That's one of my dogs. His eyes are hotter because they're not insulated by his fur, also with his nose. You can also see a reflection in the smooth floor because infrared light interacts differently with matter than normal light. One of the things that we like to think about is emissivity. So these two cans are the same temperature, but they look different with the camera because this one is very shiny in the infrared and a lot of light is reflecting off of it. So the temperatures that we're seeing here are not because of the can, but instead because of the things around it. It's reflecting infrared light, and we're detecting the reflections. This one I put tape on, even though it's the same temperature, and we're getting a better measure of the actual temperature of the camera because it has what is it backwards? It's a high emissivity. Yeah, I think that's right. I don't know why I can't think of that right now. And you can see my hand when I come near those, my hand is reflecting in the camera. Here's, I'm not sure why I did this. This is pouring coffee from a coffee pot just for fun. And you can see that the cup gets warmer and that changes temperature, and you can see reflection in the bottom. You can see all these things are hot. The coffee itself is so hot, it's beyond the scale of the thermometer, the infrared camera that I set. You can change that, but that's that. Cool. Here is one of the important things you can see when he breathes in with his mask. What happens when he breathes in is the water vapor on the mask evaporates. And you can always detect water with an infrared camera because it's always cooler. When water evaporates, it cools things off, and you can see that very easily. When he exhales, it's hot air from his lungs, and that makes it brighter. I'm not sure why I took this picture, but that's my house. Here's a fan. Fans don't cool things off. Fans make things hotter because they have an electric motor in there. They cool off humans because humans have sweat on them. Here's me in the window. You can see the window acts as a mirror, it reflects. Here is where someone was sitting on the couch, and the couch is still warm, and you can detect that. There's the rotor of a brake wheel, a wheel rotor, and it's hot after it breaks. Here is me with friction. You can see that gets hot. There's so many cool things you can see with the infrared camera. That's why everyone has to have one. There's my dog again. There are 4 lights here. This is an incandescent LED compact fluorescent. Notice that those aren't hot at all. That's what makes the LED so awesome. Here's hot water in a sink. This one's, it's kind of cool. You can see it looks like lava. And then I try to be a good person and wash it, but and then if you turn to cold water, you can see the different temperatures. And you can see where it got water everywhere too. I already showed you that one. Okay, that's it. Link to Veritasium down below. That was the only one I said I would do. Okay, that's it. The end.